Thank you. Bye. Okay, so welcome to the new chapter in CMPE59G on NanoNetworking. This is a new chapter added to the video lectures also on YouTube. This lecture will be given by Bayram Akdeniz. He's from the W department in Boğaziçi University, working with Professor Emre Pusane, and he's also a member of our research group in NanoNetworking. So,
thank you. Okay, welcome to my presentation. My topic is the major challenges in molecular communication via diffusion. Firstly, I'm going to introduce you about the molecular communication channel. Then I'm going to mention about the major challenges in this channel and the possible solutions in the literature. And finally, I'm going to present our proposed solutions to these problems, our proposed and published solutions. And then finally, I'm going to conclude all of the stuff. Okay, firstly, let's define the molecular communication channel. In fact, there are very different channel models in this literature, but it has a common property, which is conveying the information using messenger molecules. Whatever the information is, it's binding to the molecules, and the receivers capture, absorb, or observe these molecules and makes a decision about what's the intended symbol coming from the transmitter. This is the most basic property of the whole of the channels. There are many different types of channels, like it can be categorized into receiver type. Receiver can either absorb the incoming molecules or just observe and let them make diffusion again, or just absorb and capture the molecules, or another channel type can be categorized into the dimension. It could be 1D, 2D, 3D, and etc. But all of them has a common property. Information is encoded with molecules, and these molecules diffuse through the environment under the diffusion process. And due to this, it has a major problem. Molecules move very slowly. They do not move only slowly, but also they move randomly. Okay, maybe it's beneficial to sketch it. Assume that this is my transmitter, and I release molecules. This is just a molecule, and this is the receiver. The movement of this molecule is totally random with 0 mean and 2D delta t. Delta t means a time instant, a time step, and 2D comes from the diffusion coefficient, and it says that this molecule can even go to the receiver or can go back to the transmitter. Okay? Due to this randomness, it's even slower. Therefore, some of the problems arises. Let's focus on this. Sorry. Okay. Firstly, we figure out the distribution of absorbed molecules with respect to time. The x-axis corresponds to time, and y-axis corresponds to the probability of absorption. As you see, it has a peak value, and then it's decaying, but it's never becomes 0. If we extend this x line, we will see that it's never becomes 0. And we can discretize this function with discrete time steps. For instance, let's take time slot, which corresponds to the time required to transmit a symbol with 0.1 second. So this means that the transmitter and receiver communicate in each 0.1 second, and this means that only this part of the molecules is used for decoding, and the rest part of the molecules comes from the previous symbols, and they do not give any meaningful information about the intended symbol. And these all have detrimental effects. right? And due to these guys, except these, all these guys causes some detrimental problems. Okay, let's focus on in more detail into the problems of the molecular communication. The first one, as I mentioned, is intersymbol interference. All these guys except the first one corresponds to intersymbol interference. So in the many part of the literature focus on how to eliminate these ones. Another one is, as distance increases between the transmitter and the receiver, the number of reaching molecules reduces drastically with the square of t. If you increase the distance, it's almost impossible to communicate. For instance, if you double this distance for this simulation, this one will become even smaller than all of them. So we need to change our communication system or propose some other solutions, as we will see in the following slides. Another one is data rate. Data rate is so low. As you see, we choose transmission slot with 0.1 second, and this corresponds to 10 bits per second, which is so funny if you compare with the conventional communication systems. And even for this data rate, as you see, there are many intersymbol interference problems. Another problem is self-interference. This problem occurs when two-way communication is established if both are transceiver, both are absorb and receive molecules for decoding information. For instance, consider the nanomachine X. X releases molecules, and if simultaneously absorb molecules, it can absorb its own molecules. And these absorbed molecules by itself can be considered as self-interference. This is another problem. And one another concern that we need to think is computational capability of the transmitter and receiver, because they are very teeny devices, and since they are so teeny, they are not as talented as our mobile phones. Of course, you can propose many solutions that as you do in the electromagnetic communication, but in practice, they may not be applicable. Okay? And now we are starting to consider the possible solutions how to combat intersymbol interference. Okay. Maybe it's beneficial to draw here to the previous slide. Blah, blah, blah. Okay. This is the channel impulse response of any channel. Okay, impulse response of any channel. This means that in the first step, we have a portion of the received signal, and in all these steps coming from the previous symbols, because we chose the transmission slot with 0.1 second. Okay, and all these ones is considered as intersymbol interference. Okay, in order to reduce this intersymbol interference, what can we propose? How can we reduce this intersymbol interference? Do you have a trivial idea?
Maybe we can put bonds to all of the molecules and we will destroy them after, let's say, 0.1 seconds.
Bonds.
We will put bonds.
Okay, but the communication is continuous. Okay, for 1 bit it's okay, but you have to communicate continuously. So at 0.2 seconds you transmit another symbol. So okay, if just want to transmit 1 bit or 1 message, it's okay, but for continuous transmission, this is not applicable. One straightforward solution is, okay, instead of 0.1 second, let's communicate with 0.2 second. Then what happens? These two guys combine with each other. These two guys combine with each other. Let's say 0.2, 0.1, 0.05, 0.04, 0.02, 0.01. If we change the transmission slot, as you see, this is 0.3, this is 0.09, and 0.03. We have a more powerful signal and less ISI, right? Okay, that's good, but what's the cost there?
We lose the rate.
Sorry?
We lose the data rate.
Yes, we lose the data rate. Data rate is halved from 0.1 to 0.2, 5 bits per second. This is a problem, right? Oh, where did we fly? Okay. Okay, this is a solution, but in fact a trivial solution. Another one is using multiple types of molecules. Multiple types of molecules can be considered as orthogonal channels. If you use two different types of molecules, let's say A type and B type, and assuming that receiver can distinguish these molecules A and B, it can decode two different symbols simultaneously. Therefore, you can also use another channel, right? And when you use another channel, for equal data rate constraint, you can have this channel. You can have this impulse response, right? For equal data rate, if you use two different types of molecules. Is this clear? You just use two orthogonal channels, and therefore for equal data rate constraint, this turns to that. This is another trivial solution. It can be proposed, but what's the drawback of this solution? It increases the complexity, because in that case, your receiver should distinguish the type A and type B. So it needs different types of receiver. Therefore, you need to take into account this. Okay, using different types of molecules increases the performance, but it also increases the complexity. So in the near future, if we apply these solutions, maybe these are not applicable in the near future. So we need to take into account this. And okay, another one is adapting conventional equalization methods to that channel, like maybe maximum likelihood estimation or some other ones. Okay, these are applicable, and there are many published work in the literature, but this also increases the computational complexity. Okay. And other than this, we propose another method which is simple, based on shaping the pulse of the release molecules, and it requires without any computational complexity. We'll present this in the following slide, so I'm skipping it. Okay, and the other problem is self-interference. Okay, in the self-interference, as I mentioned before, transmitter, if both of them are communicate with each other, this is, let's say, A, this is B, the release molecules can be absorbed with the nanomachine A itself, and this leads to self-interference. In order to get rid of self-interference, what can we propose? Maybe considering the following solutions. What can we propose to eliminate self-interference? Just self-interference.
Maybe we can change the type of the surface for a nanomachine. Well, we can say instead of absorbing, we can say it's reflecting.
Yes, this is one solution. So you said that in one time slot, communication direction in this way, and in next time slot, communication direction that way. Yes, this is applicable. We'll present such a work. This is good, but what's the drawback behind this?
Complexity increases.
It's half duplex.
Yeah, it's half duplex and data rate is reduced. Right? Because only this time, yeah, okay, you see the point, right? But this is one solution. What if you are allowed to use two types of molecules? Can you propose something to eliminate self-interference? You have two different types of molecules.
If A nanomachine uses A and only receives B, then
Yes.
the problem is solved.
Yes. If you are allowed to use two different types of molecules, A uses type A molecule for transmission, and B uses B for transmission, and A captures B for reception, then no self-interference occurred. This is another solution. And using these two concepts, we propose another work with also estimator that we will see in the following slide. So I'm also skipping this. Okay, another problem is distance. As the distance between the transmitter and receiver is too high, almost no molecules can be received by the receiver. So in order to get rid of this problem, one of the trivial solutions is keeping symbol duration high. In practice, if you keep symbol duration infinite, you capture almost all of the molecules for some channels. Okay, this is trivial. Keep symbol duration high, you get the whole benefit, but you lose the data rate. Another solution is using relays between transmission and receiver. Therefore, these receivers get the data from gets the symbol from its neighbor and then forward it to another node. And we will discuss this in the following slides. Okay. Let's move on. And another problem, data rate. In order to combat with data rate issue, one can propose, let's use multi-level communication. I mean, instead of binary communication, if we use 4-level communication, we can send 2 bits. Or 8-level communication, we can send 3 bits. This is meaningful, this is logical, but there's a problem because when the receiver absorbs its molecules, the number of these absorbed molecules is modeled with Gaussian distribution. Maybe you have seen in the previous lectures. Receiver has a Gaussian distribution. And if we divide it with multi-level, we will have an erroneous decoding. Even it's worse than binary for many cases. And there are some published papers that discuss about the binary level and multi-level performance, and it shows that in molecular communication, multi-level communication related to concentration is not applicable. Even if you gain the data rate and for equal data rate constraint, you will have a better channel for multi-level communication, but even for the better channel impulse response, bit error rate is still not good as the binary level. Therefore, this idea is not working yet for molecular communication. Another work is using molecules like isomers that can represent more bits. You can put more bits to your molecule, more molecules to your isomer structure, and each one represents different informations. This is a promising approach if it's applicable. one of our friends is working on this area. And also we propose another work, network coding, to get rid of data rate issue. We will present this idea in the following slides. Okay. Now, in that part, we are starting to present our works. We are going to present 3 different works. The first one is related to how to eliminate or how to decrease the inter-symbol interference in the channel. And this work has been accepted for publication in communication letters. It's a receiver-based approach that finds optimum delay to reduce the inter-symbol interference without any additional complexity other than conventional CSK, concentration shift keying. This has same complexity with concentration shift keying, and it reduces the ISI. Okay, the major logic behind our approach is as follows. This is the impulse response of the channel. For a moment, assume that 250 is our transmission slot. The receiver and transmitter communicates with 250 milliseconds in each 250 milliseconds. Okay? So, in conventional CSK, transmitter releases at time instance 0, and receiver observes molecule between 0 and time slot and makes a decision. And then the next bit is transmitted at TS and makes a decision. A decision is made between TS and 2TS and so on. We propose that we first realize that, at the beginning of the time slot, almost no molecules absorbed by the receiver. As you see, there is a tau prime value that no molecules is absorbed, and as you see, there is a tau value that a limited amount of molecules is absorbed. Therefore, what if we shift the decision interval with tau second? Can we obtain a better performance? This is the concept. And of course, as you see, if tau is excessively increased, let's say if tau is 150 milliseconds, then you see this part will be ignored, and even lower signal power is obtained. Therefore, there is a trade-off. So our duty is finding the optimum tau. As you see, this area, which corresponds to signal power, is potentially higher than the area starting from 0 to 250. Therefore, our duty is finding the maximum area that can be obtained for signal power, and also inter-symbol interference.
So we increase our tap, let's say.
Yeah.
Channel tap.
Yes. In order to find tau mathematically, we should define the channel taps again. But before, first we need to define our channel. As I said in the beginning of this slides, we have many different channel models. And in this paper, our channel model is maybe the most common one, a point transmitter and a spherical receiver, spherical absorbing receiver, sorry, I forgot to add this, spherical absorbing receiver, which is R0 away from the point transmitter, and the radius of the receiver is RR. And the cumulative distribution of that channel is available analytically here. And this function corresponds to the fraction of the absorbed molecules until time t. Okay? If you are asked to find what percentage of the molecules are absorbed until 0.5 seconds, you put here as 0.5 seconds and you observe the percentage. Okay? And using this function, we can find the channel taps. For instance, between 0 and TS, you just put TS here and find the first tap, P1.
Can I ask a question?
Mm-hmm.
Can you go back to the previous slide?
Sure. Sorry.
This is for the 1D, right?
No. This is for 3D,
3D.
but it's cumulative distribution.
Okay.
If it's 1D, there is no RR here,
Yeah.
radius, right? But it's quite similar. In 1D, I think only difference is this is not included, and okay, I couldn't memorize, but it's quite similar to each other, so you are right to confuse. Okay, let's define the channel taps again. Firstly, in conventional TSK, the first channel tap that is obtained by putting TS here, because at time 0, no molecule is absorbed. So just we put TS here and find the first tap. For the second tap, which is equivalent to the fraction of absorbed molecules between 2TS and TS, we just put 2TS here and subtract it with TS. Right? I mean, until 0.1 we obtain 0.2 as a fraction. Until 0.2 we obtain 0.3. So in order to find this step, we subtract from 0.3 to 0.2. Right? And similarly for our proposed method, since we shift with tau, all the function is shifted with tau. Okay? Could you follow until there? Okay. And we are going to propose some metrics to find the optimum tau. Okay? What can we propose for comparison or for finding the optimum in communication sense? What are the metrics?
Take a derivative.
Sorry?
Take a derivative.
How can we define that, okay, this channel is a good channel?
Oh, the lesser the ISI?
Okay, yes, but at the end of the day, what you should obtain? Bit error rate. Yeah, yes, bit error rate is our ultimate goal. And okay, one solution is finding the bit error rate formula and then taking the derivative of it and equating it to 0 and finding the optimum tau. This is one solution. But unfortunately, in molecular communication literature with many memory, analytical representation of bit error rate is not available. For 2-tap, I mean for like this channel, you can propose a bit error rate formula. But this is not a realistic approach. But in the real case, you have infinitely many taps. And even the smaller taps have effect on the decoding for continuous transmission. Therefore, this is still an open problem to find a bit error rate. Maybe one of you can find and propose, and we can get more comfortable. But unfortunately, we couldn't use BER analytically. We can use BER if we use exhaustive simulations. You simulate with increasing tau with maybe 1 millisecond or with more resolution, obtain the BER for corresponding tau, recording it, and then find the minimum one. Okay, this is one solution. But instead of that, in the literature, there are some other metrics that is used in Molcom metrics, also in some other communication literature. The first one is signal to interference ratio. Our aim is maximizing this while minimizing that. Okay? So this is another metric that we could use. And we have analytical representation of this one and that one.
So for the signal to interference ratio, we are trying to increase the signal by increasing the first channel tap.
Yes.
While trying to decrease the summation of the remaining
channel
taps that cause the interference.
Yes. And this is a good alternative, and it's frequently used in the literature. And the problem here is, okay, we have a high SIR value, but there's a possibility that H1 can be excessively decreased. I mean, if this part is almost zero, whatever this one is, we have an infinite SIR. But this can also be quite low, right? And if both numerator and denominator are quite low, but if the H1 is bigger, we will have a higher SIR value. But we have a quite low signal power. Let's show in there. Instead of this channel, we would have like that. 0.01, 0.0001, blah blah blah. Therefore, our SIR here is 0.01 divided with maybe 0.001, for instance, and this corresponds to 100. Okay, it's good, but note that the signal power is quite low, right? So it may not work. So for some cases, it works for many of the cases, but it may not work for some cases. Since our ambition is maximizing this, this can be occurred somehow. Okay, this is a problem.
So the problem is that signal to interference ratio is good, but the first channel tap is so small that it would be almost impossible for us to detect that very low channel tap.
Yes, yes, absolutely. Okay, so in this paper we propose another metric that increases the channel signal tap and reduces the ISI tap without excessive decreasing in the signal tap. Do you have any idea how can we do this? Instead of dividing, what can we propose for that achieve also maximizing H1 and minimizing intersymbol interference, but also avoids for excessive decrease of H1? Instead of division,
Taking logarithm.
if you take the logarithm, okay, very good, very good. If you take the logarithm of this, what we have? We have a difference.
Yes, we will have a difference.
Yeah, okay. But instead of that, this is a good idea. Instead of that, we directly propose the difference of them. Okay, because why do we choose that? If you take the logarithm of this guy, as you see, this is a function, right? The difference of that function, and take off the logarithm of it, and then find the take the derivative to find the optimum is make it more complicated. Therefore, we just choose the difference of them. This function also increases the signal tap or decreases the ISI, but also keeps that H1 is not as small as the SIR case, because then it can turn to negative or almost zero, right? Okay, look this scenario. In this case, SIR here is higher than this, right? But if you subtract, you obtain 0.01. Okay? In the other channel, you will not obtain like that because you subtract. Okay? And we write H1 and H2 other HKs explicitly, and then taking the derivative of it and making some mathematical manipulations on this function, and then taking the equate that to 0 and obtain the optimum tau. And then compare it with optimum bit error rate, optimum signal to interference ratio, and optimum SID value as follows. The black one corresponds to the conventional concentration shift keying performance. And as you see, as we expect, we have a better performance if we shift the decision interval. We expect this, right? And furthermore, the analytical solution that we propose with SID is can have almost same bear curves and almost same tau values with the best bear curve obtained by exhaustive simulations, and also with the SIR values. Okay, in these two cases, SIR still works, but in some cases it may not work. Okay, and as you see, there is not any additional complexity compared to conventional CSK. We just shift the interval, and we have a quite better communication performance. Okay. Okay, this is the end of the first paper. Our next paper is two-way communication systems in molecular communication. In this paper, we examine the basic two-way communication systems. And when two-way communication system is considered, self-interference reveals an additional problem. And we investigate three different communication schemes to overcome this issue, and also inter-symbol interference problem. Oh, sorry. Okay. As we discussed before, assume that we only have one type of molecules. One type of molecule. Okay? Can nanomachines communicate with each other simultaneously with this one type of molecule?
No.
No. Why? Because, as I drew before, let's say this is X, this is Y. If they simultaneously transmit their molecules, and if they are same type, since molecules move very slowly, its receptors can absorb these molecules immediately, and therefore a self-interference can occur. If, again, let me repeat, if one type of molecule is available and if they communicate with simultaneously, it can, both of them can receive its own molecules immediately, and self-interference occur. And as one of your friends said that, what if we can communicate with half duplex? I mean, in the first time slot, communication distance in that direction, and in the second time slot, communication direction in this direction. This is okay. This is acceptable, and we are starting in this idea, and then trying to enhance it. Okay. Okay, let me repeat. In the first time slot in 0 and TS, X and Y, its symbol with A-type molecule, and the second instant TS and 2TS, Y send its symbol to X with A-type molecule, and so on. Okay? This is a half-duplex communication. A single molecule, since we use one-type molecule, half-duplex communication. Okay, and in such scheme, we do not only have inter-signal to ISI taps related to ISI, but also taps related to self-interference. And as you see, even though it's half-duplex, the self-interference is higher than the signal tap. Okay? And this has a detrimental effect on decoding of this signal, and we have a problem here. Okay, remember, we have a half-duplex signal, half-duplex communication, and even if it's half-duplex, we have a self-interference. Why we only have blue taps on the odd slots? Why not we have here? The blue ones corresponds to inter-symbol interference, and the red ones corresponds to self-interference. Do you get why we have such figure? Let's move on to the table. In in the odd time slots, as you see, the consider x to y channel. In the first time slot and 2 time slot, x transmits, and in the second and fourth, x receive, right? And as you see, in the third one, it does not receive anything. It sends, right? So in the odd slots, it does not receive any molecule that corresponds to intersymbol interference. But it receives its own symbol here. Okay? Therefore, we only have at the odd tops of the channel ISI and the even tops of the channel self-interference. Okay? And we have a combined version of them. At the receiver, it cannot distinguish which one is ISI, which one is self-interference, because it's all the same type of molecules. But do you find any difference between self-interference and intersymbol interference? Note that we do not know what causes intersymbol interference. We just predict. We decode the symbol, we decode the previous symbols, and we said that, okay, ISI comes from these symbols. But our decoding may be erroneously, and our assumption may not be correct. But for the self-interference cases, we exactly know which symbol causes self-interference, because it's our own symbols, right? So this is a valuable information. We know what causes intersymbol interference. And also, if we assume that we know the channel characteristic and we know all these channel taps, let's name this as P2, P4, P6, and etc. We all know this value, right? We know our own previous symbols, and assuming that we know the channel taps, we know this value, and this is used for modeling the self-interference distribution. As I mentioned before, the absorbed molecules can be distributed with Gaussian distribution. Maybe you have previously seen in the lecture, but let me refresh it. Assuming that you transmit m molecules to the environment, okay? And assume that these all molecules can be absorbed with a probability of P1, okay? So how can we model this? This is a binomial distribution, right? For instance, you toss a coin, okay, and count how many head or tail. If you throw it with 100 times, and if you are asked to find the distribution of it, you will say that it's a binomial distribution. Okay, but in molecular communication literature, binomial distribution is not used frequently. Instead, Poisson and Gaussian distribution are frequently used because it's more tractable for some derivations, and therefore, if our probability is PSI or P or something like that, its distribution can be observed in this manner: m times PSI with mean, and m times PSI with mean, and m times PSI times 1 minus PSI with variance. Okay, this is the distribution of the absorbed molecules. Okay, and if we know this, welcome. Okay, this can be considered as ISI. Okay, it's come later. Okay, if we know this, we can estimate the distribution of the self-interference. We just made an estimate, not a distribution, but just an estimation, which is m times all these. And as you see, it corresponds to the mean of the exact distribution of the self-interference, which is an unbiased estimation. Okay? We know what causes self-interference, what are the symbols. If we know the channel taps exactly, we can estimate the mean of the self-interference directly. Okay? Okay, this is one sham, and the other one is using two molecules with full duplex communication. As some of your friends suggest, this is a full duplex communication, and in each time slot, X transmits Y is symbol with A-type molecule, and Y transmits is symbol with B-type molecule to X. And thanks to this shim, we do not have any self-interference. Right? Because nanomachine X does not absorb type A and Y does not absorb type B. Therefore, there is no self-interference. But note that this communication is equivalent to conventional concentration shift scaling in two-way. Right? We do not improve anything for here. We just propose that there is no self-interference for this case, right? Okay, considering these two methods, can we do a better method for using two types of molecules in two-way communication? You are allowed to use two different types of molecules. Can we do better, which has a higher performance than this? The answer is obviously yes, but okay, it's harder to see for these two presentations. But what if we change the use of the types of molecules as follows? In the first slot, X use A-type molecule and Y use B-type molecule for transmission, and then it changed the use of the molecules. Okay? And so on. This trend goes like that. In this case, firstly we have self-interference. Note that in the previous case, we do not have self-interference. We only have intersymbol interference. But in this case, we also have self-interference. Again, we have intersymbol interference. So where is the advantage? We can use the idea of the half-duplex to estimate the self-interference. This is the one advantage, because in this case there is no self-interference, so we cannot use the previous idea. Okay, we can estimate the self-interference like that. What else? Since we changed the use of the absorbed molecules in the successive communication, we eliminate the intersymbol interference in the second taps or the even taps. Because as you see, each nanomachine only absorbs same type of molecules in odd or even taps. As you see, in this time it absorbs A-type molecule, and in the next step it absorbs B-type molecule. Therefore, we eliminate the ISI in the even parts of the channel. We only have self-interference at the even taps, and intersymbol interference only have at the odd taps. Okay? And as you see, these can be estimated, and we only have problematic at the odd taps, but we cannot show that which one is better still. We either need to derive its bit error rate formulas, which is not still derived, as I mentioned before. Therefore, we use Monte Carlo simulations to evaluate which one is the better. We expect that the half duplex is the worst one, because it uses one type of molecule and it's a half duplex. So full duplex versions will be expected that they are quite better than the half duplex. But in order to compare the latter two one, we are using Monte Carlo simulation. The first one is the half duplex, and the other one is two molecule full duplex, and the blue one is flip two molecule full duplex, which was the last one. And as you see, it has a better performance. Okay, let me summarize this paper. We just examined the basic two-way communication systems. One is the half duplex, the other one is full duplex that uses two different types of molecules, and the other one is flipped full duplex that changed the use of the types of molecules. We propose how to estimate the self-interference. In the half duplex case, we could not use this method in the two molecule full duplex case, but we can use it on the flip two molecule full duplex case. We can estimate the self-interference here. Therefore, we have a better performance. In this case, there is no self-interference, but more ISI. In that case, there is both self-interference and inter-symbol interference, but we can estimate self-interference. Therefore, it's better. Okay? Now, the last paper, we propose what if the distance between the transmitter and the receiver is so high? As we mentioned before, we will use a relay. Okay. There are many approaches that use relay between transmitter and the receiver. One method is directly decode and forward method. In this method, A transmits its message to R, and then R transmits its message to B. And then B transmits its message to R, R to A. Okay, as you see in this table. This is a decode and forward method. It's applied for all other parts of the communication literature. Not only molecular communication, but all other network parts of the communication. Let me repeat. In the first time slot, R transmits message to R. In the second one, R transmits this decoded message to B. Now, R transmits its message to B. It's okay. And in the next two time slots, B does same operation. This should be A, I think, sorry. B transmits message to R, and R transmits its message to B. And both A and B are happy. Okay? Again, for this system, what are the problems here? Note that we still have self-interference. A transmits its message to R. R transmits its message to B, right? And then these are changed, but R can absorb its own sent message to B when decoding the B's message, right? So self-interference is still here, still available here. Okay. Now I'm presenting another work in the literature that is proposed by some other researchers. It proposed that what if we apply conventional network coding method instead of decode and forward. It's proposed that, okay, let A transpose its message to R, and B transpose its message to R again later. Once relay decodes these two messages, let XOR them and send this message to both A and B. Okay? Instead of individual message, let's send them XOR of the combined version of the message. Could you decode, knowing this information, could you decode the intended symbol?
No.
Why?
Because
yes,
no.
Yes, it's either 1 or 0, but it's just XOR, right? XOR of my message and the other nanomachine message. but I know my message.
Yeah.
If I know my message, and if I get this, I can estimate this, right? How? Just XORing with my message, because new I XOR new I is 0. 0 XOR something is something, right? Okay, what are the benefits here? What is the benefits here, in fact?
We can transmit to a larger distance.
Yes, but compared to that, this can also transmit larger distance. Yes, this is one advantage, you are right, but compared to the decode and forward, what is the advantage here?
He used only 3 times slot.
Yes.
So,
Note that in the previous one, we required 4 times slot for transmission between each other, but in this case, we use 3 times slots. So for under the equal data rate constraint, we will have a better channel here, and we will expect that a better performance. Okay? This is an elegant method proposed to increase the performance. Considering this idea, this is the probability of error cases. Okay, let me briefly discuss about it. How can we obtain an error here? There is 2 cases. In this case, in the first case, when the XORed signal is erroneous, but at least one of the non-message decodes this message correctly. I mean, if this is if R decodes this message with error, and if B decodes this release message with no error, then A or B makes an error. Or VI can be decoded correctly, but at least one of the non-messages fails to decode VI correctly. I mean, okay, this is correctly decoded and released, but receiver either A or B decoded incorrectly. So let's write these 2 cases. In the first case, okay, assume that the intended symbol VI is decoded incorrectly, which is PER, times at least one of the non-messages decodes VI correctly. At least means it can be either 1 incorrect or 2, either 1 correct or 2 correct decoding. So in the 1 correct decoding, it corresponds to PM minus 1 minus PM. We have 2 different cases for here, so we add here a 2, or both of them decoded correctly, which is the 1 minus PM square. This is the first case. In the second case, when VI is decoded correctly, which is 1 minus PER, times at least one of the non-messages fails to decode VI correctly. At least one of the non-messages fails to decode correctly means that both of them can decode incorrectly, which is PEM square, or at least one, or just one of them decodes incorrectly, which is 1 minus PM times PM times 2. This 2 comes from either A or B. Okay, we have 2 different cases. So instead of dealing with this function, we just ignore the quadratic term to find a simpler lower bound. Okay. Now, it's time to mention about our proposed methods to enhance this idea. Note that in this method, relay does not need to know VI or UI. It needs to know just what is the XOR of them. Okay? So, if A and B share their own message simultaneously, can R make a decision about VI? Assume that they are sent their molecules simultaneously. Can R make a decision what is the XOR of them?
Yes, with 2-level threshold.
Yes, okay, maybe I should do a 2-level presentation, but okay. Yes, with 2-level thresholding, we can find the XOR of them. How? Because, okay, let's imagine if both of them are 1, okay? Both A and B sends M molecules to relay. If any of them, if just one of them is 1 and the other one is 0, the nanomachine that sends one release M molecule, the other one sends no molecule. Okay? And if both of them release 0 message, both of them release no molecule, right? These are the 3 cases. So if we define these 2 levels correctly, we can obtain the XOR of these 2 messages. We have a penalty that, as I mentioned before, multi-level have a worse effect on the decoding, but we are going to compare them. In this case, A sends this message to R, B sends its message to R simultaneously, and R sends the XOR version of them to B. Therefore, we reduce time slot to 2. So, and for equal data rate constraint, these time slots are increased. For achieving transmission with 3TS, we have a better channel here. Okay? And in order to compare their performances, in the paper we propose analytical probability of error bounds for 2-tap channel. As I mentioned before, such approach may not be applicable, but since in the previous paper it's proposed in this manner, we propose to show that this method is better than the previous one. And then we use Monte Carlo simulations that use consecutive transmissions for almost infinite tap channels to evaluate their real performances. Okay, but we propose another method. This method is called as half-duplex network coding, because in the one slot only A and B transmit, and in the next slot R transmits its XOR message to A and B. And note that in this case, still both interference and self-interference occurs, because we have one type of molecule available, and since both A, R, and B both send and receive message, they can all have self-interference also.
I have a question here. How do you decide the WI, the XOR of these 2 symbols, by a simple thresholding?
Yeah. The relay absorbs a number of molecules. Okay, and it says that. Okay, sorry, let me change the pen. This is the threshold 1. This is the threshold 2. If the number of absorbed molecules, let's say it's X is between these 2 thresholds, this means that only one of the nanomachines release molecule and the other one does not release. So I should decide it as 1. The XOR of them is 1. If it's higher than threshold tau 1 or lower than tau 2, this means that either both of them is 1 or both of them is 0. Therefore, I should decide the XOR version of them as 0. Okay, again, let me repeat. Both intersymbol interference and self-interference still occurs for the all cases. Okay, we propose another method, which is full duplex network coding, and in this case we use additional type of molecule, and in the uplink, I mean from AB to R, we use A-type molecule, and the downlink we use another type of molecule, and this leads us to have a 2 orthogonal channel. If we have 2 orthogonal channel with each other, what we reduce we kill the self-interference. I mean, let me erase this. Okay. Okay, hopefully it's working. Okay. In this channel, we use A type of molecules. for instance, and in this channel we use B type of molecules. Therefore, self-interference is eliminated. Okay? But we also have another benefit. Since these are orthogonal channels, we can transmit them simultaneously. Right? Therefore, compared to the previous one, for equal data rate constraint, now we can transmit our message with 3TS under the equal data rate constraint. Okay, we are using multiple types of molecules, so we expect that performance, but we also kill the self-interference. And if we compare it with Monte Carlo simulations, as you see, the blue one is the blue one corresponds to the proposed method, which is conventional network coding by another researchers, and the red one corresponds to our half duplex method, and the pink one corresponds to the full duplex simulation. As you see, it's far better than, even if these values are not so low compared to the conventional communication systems. Unfortunately, the bare values are typical for molecular communication, such bare values. Therefore, we enhance the performance of the communication when we apply different versions of the network coding. Therefore, the main logic is this. Can we get a gain from the data rate, or can we get a gain from, can we eliminate self-interference or ISI? Okay, let's try it. Unfortunately, for many cases, we do not have an analytical representation. Therefore, we need to simulate it with Monte Carlo simulations to compare which one is the better. Okay, you have some intuitive estimation, intuitive prediction about which one is better, but at the end of the day, you have to simulate and show which one is better. Okay, let me conclude. Molecular communication is a new research area. It's like a baby, newborn baby. We try to teach him how to run, how to speak, how to eat. Maybe it's a very newborn area, and it has many open problems still untouched. And we have some problems. First, the transmitter and receiver are teeny devices, so it's not as capable as mobile phones or some other receivers, some other transceivers in the conventional communication systems. And also, since the molecules move very slowly, data rate, communication range, and interference are the major challenges. Okay, these are also a problem in the conventional communication systems, but in molecular communication, these are more major than the other systems. And if you propose a solution with low complexity, you have a higher chance to both publish it, and also in the near future, it can also be used as an application. Okay, these are the references that I used for the representation. You are welcome if you have a connection. That's the end of my presentation. Thanks for listening to me.
I have a question. When you are talking about self-interference, and you say, I can estimate, because I am sending that message.
Yes.
Do you change your decision criteria?
Sorry?
Based on your, do you change, because I have a decision criteria, right? If I receive that amount of molecules, I say 0.
Yes, I change.
If I not,
yes, I got the point. Yeah.
So should you change your?
Yeah, this is a good point to ask. Maybe I should add an item to. Okay, when I estimate this for each transmission slot, I change my decision threshold based on this estimation.
You should change.
Yeah, I should change, because
so it's easy.
Yes, yeah, it should be easy. In fact, the calculation of this is maybe more complicated than changing the thresholds. Changing thresholds is just a decision, but in calculation of this requires a convolutional operation and requires some memory. Achieving this is even more.
But you should do this for every bit, right?
Yes, yes. It's something like an adaptive thresholding. Any questions?